Okay, Math 2318, linear algebra students. We're on the last week of material. Today I'm going to talk about similar matrices and diagonalization. So that's getting us from the end of section 5.2 into section 5.3. Okay, so recall that the definition of A being similar to B, that was in 5.2. And I'm using this symbol for similar to because we have already used this symbol for is row equivalent to. Okay, just one squiggle, row equivalent. I'm using two, or is similar to. So A is similar to B if and only if there exists another matrix P that is invertible such that B can be written as P inverse AP. And that definition seems to kind of come out of the blue. Who cares, right? Well, here's why you could start to care. Similar matrices have exactly the same eigenvalues. That's one good thing about it. Not the same eigenvectors, but we're going to see they're very closely related. I don't think your book emphasizes this enough, so this is different. The other thing about why it's good to be able to take use a different matrix B that is similar to A in this manner is that if we, for example, if we need to know what was happening with iterates of B, like if B represents a dynamical system, right? And you want to know what happens after many iterations of that dynamical system. So raising that to the nth power, you could prove that that same thing is raising that to the nth power. And when this is multiplied by itself, the P times P inverses are going to collapse. And you're just going to get that B to the n is the same thing as P inverse A to the n P. So if that dynamical system is easier to evaluate than this one, it's going to be very handy to have that other form. All right, but first of all, let's talk about why they have same eigenvalues exactly, but not exactly just related eigenvectors. So suppose that X is an eigenvector for A with the eigenvalue lambda. And suppose that A is similar to B. So there exists some matrix P whose P inverse we can put over here and get this. All right, well from that equation, you can get this, right? What would you have to do to that equation to get this one? You should be able to fill in the blanks on all these. To get from here to there, you would just multiply both sides of this equation on the left by P, right? P times P inverse is going to disappear, leaves with that. Well, from that, you should be able to get this by doing what? Let's see, that's PB, that's PBP. So multiply both sides on the right by P inverse. Yeah, P inverse times P, that's going to disappear. We're just left with A. All right, so if A is similar to B, then B can be written this way, but notice also A could be written that way. Now, that means if we take A and multiply it by X on the right, and multiply X on the left by A, that's the same thing as multiplying X by all that, right? Now, what have we done from here to there? Multiplied both sides on the left by P inverse, right? Okay. And what does that give us? Well, let's see. So we have BP inverse X, BP inverse, same thing here. What do we do from here to there? What's the reasoning? Let me let the cat out of the house. Goodbye. Okay, so this let the cat out of the bag. That what we're using from here to here is the fact that X is an eigenvector of A, right? So now we have BP inverse X is equal to, lambda is the scalar, can just come right out in front of that matrix. And so if we group things now, associate things, we have B times P inverse X is equal to lambda times P inverse X. Well, let Y be equal to P inverse X. Then lambda is an eigenvalue for B, because by is equal to lambda y. So lambda, that was an eigenvalue for A, is also an eigenvalue for B, but not with the same eigenvector x. Instead, it's this transformed P inverse x. So remember, we assumed in the beginning that we had some invertible matrix P. So to get the eigenvector for the similar matrix, you just take its inverse and multiply by x. If you're assuming that you're starting off with your definition of P as this one here. P inverse on the left, P on the right. Okay. So they have the same eigenvalues, very similar, but not exactly the same eigenvectors. Let's look at some similar matrices. Here's a matrix A. I'm worried about the glare here. That made it worse. Better or worse? I think it's going to be better over here. Wow. Equally bad. Let's see, how can I get to that spot? Yeah, that might have to be it. Alrighty. So, let's get your eyes up here. So, here's the matrix A. 4, 0, 1, negative 2, 1, 0, negative 2, 0, 1. And the matrix B with 1, 2, 3 on the diagonal. Yeah. Okay. And 1, 2, 3 on the diagonal. Okay, you can't see that. All right. And if we take P to be equal to this matrix, what is that? That glare is not going away. That is read as 0, 1, 0, negative 1, 2, 2, negative 1, 1, 1. Okay. And so, well, how could we verify, without finding P inverse, that B is equal to P inverse AP? Well, notice, if we know that P is invertible, prove P invertible easily, quickly. How would you do it? Take its determinant. If it's a square matrix and the determinant is not equal to 0, it has to be an invertible matrix by the invertible matrix theorem, right? So one, prove that P is invertible. Verify that is the case. Once you've got that, then you could take that equation here and get to this one just by multiplying both sides on the left by P, right? So then I would get PB is equal to AP, or AP is equal to PB, flopped over. Verifying that, if you have A, B, and P in front of you, then verifying this is just a matter of multiplying that times that, get something. Multiply P times B in that order, get something. Show that they're equal. Okay, so if you had to verify or not, true or false, are A and B similar using this matrix P, that's a way of doing it. Okay. Now let's come back over here. All right. So if A is similar to B, they have the same eigenvalues. That we know from the theorem. But notice that the converse is not true. If you have two matrices that have the same eigenvalues, it's not necessarily the same that they are similar. For example, let A be equal to 2, 1, 0, 2, and B equal to 2, 0, 0, 2, right? Then lambda equal to blank is the eigenvalue, the one eigenvalue for each one. Now what would that be? Well, since that's a triangular matrix, the values on the diagonal are its eigenvalues. So lambda equal to 2 is the one eigenvalue for each of those. Right, that's diagonal, that's triangular, so same thing held for both. 2 is the one eigenvalue, but they're not similar. Now to say something's not similar means that they just not exist, okay? So if you have, somebody was saying that something exists and you negate that statement, that means you're saying for all p, it's not the case that whatever follows. This is logic. For all p, invertible p, it's not the case that b could be set equal to p inverse ap. For all invertible matrices. How would you prove that? While you're thinking about that, hopefully you stopped the video and went off and proved to yourself that not only are this is the eigenvalue for both, but you went and found the eigenspaces just for fun, right? Okay, so if you did that, what have you got? For A, when you substitute in lambda equal to 2 there, right? That's for this matrix A. Subtract that. Oh yeah, that's similar to this. It's actually equal to that, excuse me. And that's equal. And that, if you look at it and ask yourself, what x, y solve that? If you have 0, 1, 0, 0, x, y equal to 0, 0, what does that tell you about x and y? Well, y has got to be equal to 0, but x, no restriction on x. So there's only one linearly independent eigenvector, 0, 1, because like we said, sorry, y is equal to 0, sorry, this should be 1, 0, my bad. X is free, y has to be 0. So that's the eigenspace for lambda equal to 2 for the matrix A. What about for B? For B look like this. Okay, well if you substitute 2 in here, then you're left with exactly this. Okay, and what does that have as solution? X could be anything, y could be anything. So that means that this eigenspace has 2 linearly independent eigenvectors. 1, 0, and 0, 1. Not to mention infinitely many others, but you could take those too, right? All right. So that difference is going to be key for how we're going to be able to, I haven't done it yet, but we are going to be able to prove this statement that for all invertible matrices P, it is not the case that B could ever be equal to P inverse AP. And that's by using the theorem 5 in section 5.3. That will be the topic of my next video.